Oblique impacts. Past exercises. A smooth sphere S of mass m moving on a smooth horizontal table with speed u strikes obliquely an identical sphere T which is at rest. The direction of motion of S before and after impact make angles alpha and 2 alpha respectively with the line of centers of the two spheres. Given the coefficient of restitution between the two spheres is E, show that 1 minus E tan 2 alpha is equals to 2 tan alpha. B, tan square alpha is equals to E. C, that tan alpha ranges from 0 to 1 and that alpha is less than or equals to pi over 4. Taking E equals to pi over 6, E, find the loss in kinetic energy due to the impact. Consider two spheres in their line of centers. U is the velocity of sphere S, while this is sphere T, which is at rest. This sketch can be drawn in the simpler form as this. This is the velocity of approach. This is the velocity of departure. This velocity makes an angle of 2 alpha with the line of centers and an angle of alpha with the line of centers. The horizontal components and the vertical component of U are U cos alpha, U sin alpha. The angle that U makes with the line of center is alpha. This alpha is the same like this angle. That's from the alternate angles. This alpha, this will be alpha. So if I apply the formula of sine in a right angle triangle, that's SOHCAHTOA, I'm going to have U cos alpha here and you have U sin alpha there. So this is the parallel component and this is the perpendicular component of sphere S. That's parallel to the line of center and perpendicular to the line of center. The velocity US of sphere S before impact is given as U cos alpha, U sin alpha. Thus, up we write the parallel components and down the perpendicular component. That's the parallel component to the line of center and down the perpendicular component to the line of center. The velocity UT of sphere T before impact is given as 0, 0 since sphere T was at rest before impact. The velocity Vs of sphere S after impact is given by x U sin alpha. In oblique impacts, motion is considered to be along the line of action. So motion is parallel. Perpendicular to the line of action, there is no motion. So the velocity perpendicular to the line of action remain the same before impact and the same after impact, since there is no motion perpendicular line of action. And the velocity parallel to the line of action changes after impact. The velocity Vt of sphere T is given by y0. Since after impact, sphere T moved from 0 when it was at rest to a velocity y which we don't know. And the velocity perpendicular to the line of action for sphere T remains 0 since there is no motion in the vertical direction or perpendicular direction, the line of centers. From the law of conservation of linear momentum, momentum before collision or momentum before impact is equals to momentum after impact. That is mus plus mut is equals to mvs plus mvt. That is mu cos alpha plus m0 is equals to mx plus my. In oblique impacts, motion is considered to be along the line of centers or parallel to the line of centers. So only the parallel vectors are considered. So here in US, I take only the parallel component, and VS I took x since it's a parallel component, and in VT I took y since it's a parallel component. Mu cos alpha is equals to mx plus my. The spheres were identical and their masses were the same. So m is common in both sides of the equation. So m cancels. I have u cos alpha is equals to x plus y. That means x plus y is equals to u cos alpha. Call this equation 1. From Newton's law of restitution, Vt minus Vs all over ut minus us is equals to negative e. So here we are also taking only parallel components. That's parallel components of velocity to the line of centers. So Vt is y, that is y minus x over ut minus us. Ut is 0 minus u cos alpha is equals to negative e. That means means y minus x is equals to EU cos alpha. Equation 2. Equation 1 minus equation 2. That is x plus y is equals to u cos alpha minus y minus x is the same like minus x plus y is equals to EU cos alpha, which is going to give me x minus minus x is the same like 2x, y minus y is 0, which is equals to u cos alpha minus EU cos alpha. That is 2x is equals to u cos alpha minus EU cos alpha. U cos alpha is common here. I factorize out. I'm going to have 2x is equals to u cos alpha into 1 minus e. That means x is equals to u cos alpha into 1 minus e divided by 2. So I replace x in the place of x in the vector vs. So vs becomes, in the place of x I put x, so I'm going to have u cos alpha into 1 minus e all over 2 u sine alpha. I was required to show that 1 minus e tan 2 alpha is equals to 2 tan alpha. Recall that if beta is an angle that a sphere makes with a line of center after collision or after impact, then by formula tan beta is equals to perpendicular component of the velocity all over the parallel component of the velocity after impact. That is, the sphere S meets an angle of 2 alpha with the line of center after impact. That means tan 2 alpha is equals to the perpendicular component of sphere S after impact, which is u sine alpha all over x, where x is the parallel component of the velocity after impact. This is a formula. That means tan 2 alpha is equals to u sine alpha all over x, which is u cos alpha into 1 minus e all over 2. If I invert the denominator, I am going to have tan 2 alpha is equals to 2u sine alpha all over u cos alpha into 1 minus e. That is, tan 2 alpha is equals to 2u sine alpha over u into 1 minus e cos alpha. Sine alpha over cos alpha is the same like tan alpha, which is the same like 2u tan alpha all over u into 1 minus e. Here u cancels, u cancel u. I'm going to have 2 tan alpha over 1 minus e. From here I have tan 2 alpha is equals to 2 tan alpha over 1 minus e. When I multiply both sides by 1 minus e, I am going to have 1 minus e into tan 2 alpha is equals to 2 tan alpha as required. That's what I was required to show. Proof ends. B. Required to show that tan square alpha is equals to e. We know that from the a part of the equation, 1 minus e tan 2 alpha is equals to 2 tan alpha. You got to recall that tan 2a is the same like tan a plus tan a all over 1 minus tan a times tan a, which is the same like 2 tan a all over 1 minus tan square a. So it means from here 1 minus e times 2 tan alpha over 1 minus tan square alpha is equals to 2 tan alpha. Dividing both sides by tan 2 alpha, you see that tan 2 tan alpha is going to cancel 2 tan alpha the other way. From here I'll have 1 minus e over 1 minus tan square alpha is equals to 1. Multiplying both sides by 1 minus tan square alpha, I'm going to have 1 minus e is equals to 1 minus tan square alpha. That means negative tan square alpha is equals to negative e. Dividing both sides by negative will give me tan square alpha will be equals to e as required, and the proof ends. C. Required to prove that tan alpha ranges from 0 to 1. We know that the coefficient coefficient of restitution E is always a value that ranges from 0 to 1. And from the B part of the question, we know tan square alpha is equals to E. This means tan square alpha ranges from 1 to 0, the same like E. If we take the square root of 0, square root of tan square alpha, square root of 1 is going to give us 0 less than or equals to tan alpha less than or equals to 1. In oblique impacts, the angle of approach is always acute. Acute means the angle of approach is always between 0 to 90 degrees. That's the angle is not up to 90, it is not less than 0. That means if I put less than or equals to sign here, it means that tan alpha was equals to 0. And if tan alpha is equals to 0, it means that alpha was 0, since tan 0 is 0, and which is not true. Alpha cannot be 0, so it's enough for me to say that 0 is less than tan alpha less than or equals to 1. That is that tan alpha was greater than 0. So to make sure that alpha was not 0, so you see it has come out as required, and the proof ends. D, required to prove that alpha is less than or equals to pi over 4. From the C part, tan alpha is from 0 to 1. That means tan alpha is greater than 1 and tan alpha is less than or equals to 1. That is, tan alpha is less than or equals to 1, which means alpha is less than or equals to tan inverse of 1. That means alpha is less than or equals to 45 degrees. Since tan inverse of 1 is 45 degrees, that means alpha is less than or equals to pi over 4. Since 45 degrees in radians is pi over 4 as required, so proof ends. E, given the coefficient of restitution as pi over 6, find the loss in kinetic energy due to the impact. Kinetic energy loss is mostly denoted E and can be gotten from the formula E is equals to half m1 m2 over 2 into m1 plus m2 into 1 minus E squared into u1 cos theta minus u2 cos alpha, where m1 is the mass of sphere 1, m2 the mass of sphere 2, E the coefficient of restitution, which is given as pi over 6, and u1 cos theta, u2 cos alpha are the parallel components of the velocities of the spheres before impact. We had the sphere S, whose parallel velocity before impact was u cos alpha, and the sphere T, whose parallel components of velocity before impact was 0. That is for S. This is for T. We know S was the sphere 1, T was sphere 2, and T was at rest. That's why the velocity is 0. I know all of them had an identical mass of m. Substituting this information in the formula, we have kinetic energy loss is equals to half m times m all over m plus m into 1 minus pi on 6 all squared into u cos alpha minus 0. That means E is equals to half m squared over 2m into 6 minus pi over 6 squared into u cos alpha minus 0, which is the same like u cos alpha. M here 1, m cancel here m. That means E is equals to 2 times 2 is 4, m over 4 into 6 minus pi over 6 all squared u cos alpha. That is, the kinetic energy loss can also be calculated using the formula kinetic energy before impact minus kinetic energy after impact. But this other formula is more easier to use. Therefore, kinetic energy loss is equals to this expression, and the unit is joules.